Hello everyone. This is homework number 5, the multiplication property of equality. And the first concept is to consider what's defined to be the reciprocal and of a number. And the reciprocal of a number is just simply a number such that the product is equal to 1. So if we have a fraction like 4/3, we say the reciprocal is 3/4. So many times students will just think of reciprocal as flip it over. And this would be because, and I'll just abbreviate, because if you take the product of the number and its reciprocal, 4/3 then times 3/4, you can see we get cancellations all over the place, right? And these are all ones when we cancel. So we get 1 over 1, or just simply 1. Now when you have a whole number such as 7, the first thing you might want to consider is writing it as a fraction. And any whole number can be written as a fraction if you just simply place it over 1. And then we could think of the reciprocal as, once again, flipping it over. So we would say the reciprocal is 1/7, and this would be because if you take 7 over 1 times 1/7, you get 1 again. Again, you do the little cancellations if you want to show them. Okay, so that leads us to what we call the multiplication property of equality. Now, we've actually used this when we've solved proportions, but formally stated, it's just saying if two things are equal, A equals B, you can multiply by some number C, or you could divide by some number C, and you would obtain equivalent equations. So remember, equivalent equations mean they have the same solution. But we do have a provision here, and this is that C is not equal to 0, because if C were equal to 0 in this situation, you cannot divide by 0. So, wrote a little comment. Basically, we can multiply or divide both sides of an equation by any non-zero number to obtain an equivalent equation. And we've seen this before. For example, when we solve proportions, if we have something like 7x equals 42, we know the easiest thing to do is just to divide by the coefficient of x. So divide both sides by 7. So we have 7x over 7, 42 over 7, and that would give us that x equals 6. Now, the reason why I went over the reciprocal concept is because, and most people do not think this way, if the coefficient is a whole number, everybody thinks of just dividing by that coefficient. I should say, instead of whole number, I should say integer, because when you want to get used to this term, an integer means, this is just a fancy term to mean the numbers 0, 1, 2, 3, and so on, and their opposites, -1, -2, -3, and so on in that direction. So if the coefficient is an integer, we would consider division, because the other approach, I'll just put a little squiggly line here, would be to use the reciprocal. And as we've just discussed, the reciprocal of 7 is 1/7. So you'd multiply both sides by 1/7. And you might even express the 42 over 1. And then these 7's on the left cancel, giving us 1x over 1, or 1x, or just simply x. And now we can divide the common factor. 7 goes into 7 once, into 42 6 times. And we get 6 over 1, or 6. So you can see it's much more complicated to think about it in that fashion. So just remember, if you have an integer as a coefficient, just simply divide. But divide by that coefficient with the sign included. So for example, in this equation, we're going to divide by -5. So you want to divide by the coefficient including its sign. See, because the idea is you want those to cancel so that you solve for x. 1x over 1 is 1x, or just simply x, and then you could do the division. So it's going to be negative, because a positive divided by a negative is a negative. And if you have to use your calculator, that's fine. I believe that's 17. Okay, so then you could have decimals involved. And also remember that the variable does not have to be on the left side. So you have to be versatile. The variable's on the right, just deal with it. So in this case, to solve for p, it's on the right hand side. I'm going to divide by its coefficient, 2.6. So 13.52 divided by the 2.6, and the 2.6p divided by 2.6 gives, and obviously you're going to use your calculator here. So 13.52 divided by 2.6 comes out to 5.2. So remember, 5.2 equals p is fine. You could say p equals 5.2. If you like. But the statement here is sufficient. Okay? Alright, now I wrote here a note. I'm going to show this answer in 2 ways. Here it's cumbersome if the coefficient of the variable is a fraction. It is cumbersome to think about dividing by the fraction. So that's where the idea of the reciprocal comes into play. So the reciprocal of 2/3 is 3/2. So I'm going to multiply both sides by 3/2. Notice how I'm putting the 3/2 in front of the quantity on either side. And since this is a whole number on the right, or an integer, I'm going to write it as a fraction by putting it over 1. And now on the left hand side, we get the cancellations. Of course, that's the property of the reciprocal, that the product is 1. So we get 1x over 1, or 1x, or just simply x. And then on the right, before we multiply, let's divide out the common factor of 2. Goes into 2 once, goes into 8 4 times. So then multiplying across, we get 3 times 4 is 12, 1 times 1 is 1, so x is 12. Now, it's fine to do it that way, but there is, I feel, an easier way, because we are all familiar with the concept of cross multiplication. So I'm going to put a little wavy line here, because this is the alternative method. So I'm going to say, or, if you start with the same equation, here's what you could do. Instead of having the x off to the right of this fractional coefficient, you can write the x in the numerator of the fraction. So it's basically your kind of, the x is absorbed into the numerator, because that's really x over 1 if you think of it. So we'll write 2x over 3 equals, and then let's make this a true proportion by putting the 8 over 1. And then we can cross multiply, and we get 2x equals 24, And now we can divide by the coefficient 2, and x is 12. So, although it may look like more steps, I think conceptually it's easier to understand. So it's your choice. Special case, if the coefficient's a fraction, either use the reciprocal approach or the cross multiplication approach. Okay, so here's just another one to practice, and I'm going to use the cross multiplication approach. So I'll let the x be absorbed into the numerator. The right hand side is 6 over 1. Cross multiply, we get 3x equals 30, and divide by 3. And we have x is 10. Okay, so the cross multiplication approach, again, I feel is easier. Sometimes the problems are set up so it's almost begging you to use cross multiplication. Like in this example, they already have the variable in the numerator of the fraction that's on the left. So if it's a whole number on the right, write it as a fraction by putting it over 1, and then we can cross multiply. 1 times a is 1a, or just simply a right away, and we get 2 times 9, or 18. Okay, so moving on. If we have an equation that's of the form ax plus b equaling c, so we have the variable on one side along with a constant term, the b for example, equaling some constant. We first want to obtain the form ax equaling d. I just used a different letter there because basically what I'm talking about doing is transposing this b to isolate the x. And we've done that before. So this is a two-step process if we see an equation of that form. For example, okay, I'm going to recopy this. 3m minus 5 is 16. I want to isolate, and we've done this before, but never with the coefficient. The coefficient was always 1 in the first unit that we saw, that we considered in homework number 4. But here the coefficient is different, so now it becomes a two-step process. First we want to isolate the variable, so we're going to get rid of the negative 5 by adding 5. And remember the structure, you want to add 5 to both sides, line up the equals, draw a nice addition bar. The 5's go away, the 3m's brought down, we don't need to write a plus 0. Just tuck that 3m right next to the equals, line up the equals and bring them down. Do the arithmetic, 16 plus 5 is 21. So that's step 1. Notice now it has the form of ax equaling d, where the variable is on one side and the number's on the other, and it's just a simple division. So these types of equations, two-step process. Move the numbers to one side, then divide. So we'll divide by 3, and m is 7. Now remember, with any of these equations, you can always perform a check. You could substitute the 7 in for m and make sure that the left side is equal to the right-hand side. But with some of the more cumbersome equations, we tend to avoid a check. Okay, now remember, be versatile. If the variable's on the right, leave it on the right and just deal with it. So here we have an equation, the variable's only on the one side. We want to isolate it. So again, I'm going to recopy. Minus 8 equals minus x plus 4. We want to isolate that minus x. So we'll have to add the opposite or subtract 4. And again, notice the structure. If we subtract 4 from one side, we subtract 4 from the other side. Line up the equals. Do the arithmetic. We get negative 12 equals negative x. And the 4's go away. No need to write a plus 0. But now, this negative x, when it was like 3m, we knew to divide by the 3. This negative x, it really means there's a negative 1 that's being multiplied by x. So we have to get rid of that by dividing by the negative 1. So negative 12 gets divided by negative 1, and negative 1x gets divided by negative 1, and negative divided by negative is a positive, so x equals 12. Now, an equivalent way, instead of dividing by negative 1, you could actually multiply by negative 1. That'll get you to the same point. But we're so used to doing the divisions that I think I'll just leave it at that. Okay, so sliding that negative 1 in there if you want could be helpful. Okay, now here's a very important concept. If the variable is on both sides of the equation, then we have to choose a side that we want to bring the variable to. And there's a general guideline that we'll consider after showing the solution to this example, but it doesn't matter what side you bring the variable to. You will get the same answer, but we're going to notice something about this situation. So here's an example where we notice the variables on both sides. So let me recopy. 8x minus 4 equals 3x plus 6. And I mentioned in the notes here, this is method 1. We're going to bring the variable to the left-hand side. If we're going to bring the variable to the left-hand side, we're going to transpose the 3x. And remember, transpose is just a term, fancy term that's used to indicate that we're moving a term from one side of the equation to the other. So get used to that because we use that term often. So I'm going to transpose the 3x by adding the opposite or subtracting 3x. Now I'm going to line up the equals, and this minus 3x I'm going to put right under the x because those are like terms. And then I show my addition bar. And then 8x minus 3x gives 5x. We'll bring down the negative 4. And that's equal to the 3x's go away. And we bring down the 6. So notice at this point we have an equation identical to the previous examples. It's now of the form ax equaling b. Or ax plus b equaling c, excuse me, where we have the variable and a constant equal to a constant. So we always want to move the variable first. And then once you get the variable on one side, you have to get the numbers on the other side. And so to isolate the 5x now, we have to eliminate this negative 4 by adding the opposite or adding 4. Lining up the equals again, showing the addition bar. The 4's go away, but bring down the 5x and tuck it right in next to the equal sign. And 6 plus 4 is 10. And now finally it's a division. So remember at this point, it's a two-step process, right? So now we're looking at this as a three-step process when we see the variables on both sides. But now we just simply divide, so we're dividing by 5. And x is 2. Now it doesn't always have to come up to be a pretty number, okay? You could get fractions as your answer, and we'll probably see that in future questions. But for right now, they're working out pretty. Okay, so now let's consider bringing the variable to the right-hand side. So again, I'll recopy 8x minus 4 equals 3x plus 6. And if I'm going to bring the variable to the right-hand side, I'm going to transpose the 8x by adding the opposite or subtracting 8x. I line up the equals, I put the minus 8x right underneath its like term of 3x. And then on the left, the 8x's go away. No need to write a 0 there. Bring down the negative 4, and that's equal to combining 3x with negative 8. We get negative, with negative 8x that is, we get negative 5x. And then we bring down the plus 6. And now if I have the variable on the right, and notice now it's a situation just like the previous example 8, where it's going to be a two-step process. Variable on one side, you want to bring the constants or the numbers to the other. So we have to transpose the positive 6 by subtracting 6. And combining a negative 4 and a negative 6, we get a negative 10. Line up the equals. That's equal to negative 5x. These 6's go away. And now we can divide. So notice how it's a three-step process when the variable's on both sides. And we finally divide. We're going to divide by the coefficient of x, sign included. So I'm dividing minus 5x by a minus 5. So I divide the minus 10 by a minus 5 as well. And a negative divided by a negative is positive. 10 divided by 5 is 2. And so we get 2 equals x, which is the same, of course, as saying that x equals 2. So you can see we get the same answer no matter which way we do it. So there is an advantage to bringing it to one side, and in particular, the advantage is, as I wrote in the guideline here, to avoid negative coefficients. Notice how when we brought it to the left in this example, the coefficient, the resulting coefficient was positive, and when we brought the variable to the right in this example, the resulting coefficient is negative. So the guideline is to avoid negative coefficients, because that's often mistakes in algebra, just careless negative sign errors. We bring the variable to the side where the coefficient is greater. Okay, so I'm going to stop right there for this part, and then we'll come back and we'll do a part 2 and reinforce that guideline and extend our concepts even further.